Hello everyone, this is Yu from class hw6. In this video, I will solve question 1 in homework 6 first. So in this question, we are given the information that x and y have a joint density function that fxy equals to 1 plus xy over a. X is ranging from -1 to 1, and y share the same range. And in other conditions, this joint density function will have the value of 0. So for the first question, find a so that the above defined joint density function is a valid joint density function. So according to the definition, we just need to integral from the infinity to the infinity and of the joint density function fxy xy dx dy equals to 1. In this question, we just need to plug this formula here to here, and this range we also need to place it in the integral here from -1 to 1, and is 1 plus xy over a dx dy equals to 1. After the calculation, I can get 4 over a equals to 1. That means a is 4. So this is part A. Now for the part 2, we need to figure out whether the random variables x and y uncorrelated or not. So according to the definition, is expectation of x and y should equals to the expectation of x and times the expectation of y. If they are equal, then that means the random variables x and y, they are uncorrelated. So let's check out whether in our situation this should be uncorrelated or not. So for this question, the expectation of x and y should equals to the integral from -1 to 1 xy times 1 plus xy over 4. 4, we just got it from part A. So dx dy, and after that we got 1 over 9 is the value of the expectation of x and y. So let's check out the right side of this equation, whether they are also 1 over 9. Let's check out the expectation of x first. From the -1 to 1 to do the integral, and x times 1 plus x times y over 4 dx dy, we can get the answer is 0. So in this case, if the right side of this equation is 0, that means it cannot be 1 over 9. They are not equal. So the random variable x and y are not uncorrelated. So this is for the part 2. Now, for the part 3, we need to check whether random variables are independent or not, because from the previous part, we have already known that x and y are not correlated. So that means they are not independent. Now for the part 2, we need to find the joint density function of x squared and y squared. Let's set z equals to x squared, w equals to y squared first, and the Jacobi metric should be 2 times x, 0, 0, 2 times y equals to 4 times x1 y. And in this situation, for x and y, we have 4 rules. And when the z is ranging from 0 to 1, and W is ranging from 0 to 1, we can get 4 roots. They are the square root of z and the positive square root of w and the negative square root of z, the positive square root of w, the positive square root of z, the negative square root of w, and the minus square root of z as well as minus square root of w. So they are the 4 roots. So according to the definition and the formula, we can calculate the joint density function of z and w. Then finally we can get the answer is 1/4 times the square root of z times w. So this is just the situation for z is between 0 and 1 as well as w is ranging from 0 and 1. In other odd conditions, this density function should equals to 0. Now for the last part, we should to check out whether the x squared, the random variables x squared and y squared, they are independent or not. So from the previous part, we have already known that the joint density function of z and w is this one is 1/4 times the square root of z times w. So how to calculate the marginal function of fzz? So it should be the integral from -1 to 1 and 1/4 times z times w, and dw it should be 1/2 times the square root of z. Similarly, we can get the marginal function of fww. So it's also the 1/2 times the square root of w. So clearly the joint density function of fzw and equals to the marginal function of fzz times fww. So that means they're independent. This is the answer for the question 1 in homework 6. Thank you.